Well, first let's have a brief idea about Lorentz force. Now, what is Lorentz force? That is, suppose here is a magnetic field. Here is a magnetic field. Now, why am I representing with a dot? This is a way of representation of any magnetic field. That is, actually this magnetic field is perpendicular to the plane of this board and towards the observer, means towards you all. So, in this magnetic field, if I place any moving charge like this, Q is any moving charge or any current carrying conductor in this magnetic field, then this will experience a force. This current carrying conductor will, or this moving charge will experience a force due to this magnetic field, and this force, remember that this force will be perpendicular to direction of both the current and the magnetic field, or this force will be perpendicular to the direction of both the velocity of the moving charge, direction of velocity of moving charge and the magnetic field. You can calculate by the formula if force equals to Q for this charge, Q into V cross B, this is cross product, or for this current carrying conductor, that is I, you can calculate the force like this, that F is equal to I into dl. L is the length of the segment. This dl actually is the length of the segment that is falling within this magnetic field, dl cross B, and dl also represents the direction of the current. Here dl I can tell like this unit length is dl. Now this dl also represents the direction of the current as well as the length of the wire, which is length of the current carrying conductor or wire, which is falling within this magnetic field. So this is a formula. Now here we don't need the formula because here I am just for representation of Lorentz force. So let's show my device. Here this is the battery, this is a switch, this is the wire, and this is the wire that is within this magnetic field, and this is the main thing that is required, of course, the magnets to create the magnetic field. I'm rotating it, see, like this. Now when I am going to turn on the current will flow from the positive to the negative. That means it will flow like this, and this is actually the north pole of the magnet. This side is the north pole of the magnet, and this side is the south pole of the magnet. So magnetic field is directed from north to south, so in this direction, and current will flow in this direction. Now there is also a way by which you can determine the direction of force, that is Fleming's left hand rule. This is the Fleming's left hand rule. This is current, this is magnetic field, and this is force. So current is flowing like this, right? Current is flowing like this, so this will be in the direction of this, in this direction, and magnetic field is in this direction, so this will be like this. This is the force, this is the current, and this is the magnetic field, like this. Now you see that this is the current, this is the direction of the magnetic field, so the force is in downward direction. So let's see whether I am right or not, or Fleming's left hand rule is right or not. And this by this device, and I can also represent the Lorentz force. So now I am going to turn on the switch, and you will see a slight movement in downward direction. Are you all ready? I am ready. See, we see if you look carefully, there is a force in there. It experiences a force in downward direction. See, when I will turn on the switch, it will go in downward direction. I'm zooming it so that you can see clearly. So you can see the slight movement. And so Fleming's left hand rule is right, and also Lorentz force.